All right, let's start talking about this Openstax physics textbook. So this is the preface. It's the beginning. It's talking about Openstax. It's a nonprofit based at Rice University to try to get textbooks out there using technology and other things to help make education more affordable to folks. The book is fully customizable, so you could, if you wanted to, take this book, copy, paste, edit, whatever you wanted to do, and then as long as you attribute what you are using. So if you wanted to create your own textbook version of this, using this as the base, you could do that. And as long as you provide attribution to OpenStax and its contributors, you are free to do so. Errata, there's some errors. If they find them, they fix them, and it's constantly being updated, which is a nice thing about using a web-based textbook. There's your format there. It's PDF or other forms. College physics is algebra-based physics thing, some algebra and trigonometry, no calculus. Don't be afraid of calculus if you have to deal with it someday. It's not a big deal. All right, so coverage and scope. What we're going to cover in this course is chapters 1 through 17, and they're listed there. And there's some parts of the book, the concepts, calculations, this modern perspective chapter thing here, and then this, let's see, so there's some, the book is, it says it can be organized and rearranged into different, each chapter is self-contained, it tries to say, but it says modules contain references to other modules, so, you know, it's better not to rearrange and modify the course as best you can. So I'm just going to go through the book from start to finish, chapters 1 through 17. Every module begins with learning objectives, so you should read those at the beginning of the chapter and just say, okay, what are we trying to learn here? And that's what you're going to be focusing on. There's these call-outs, there's key terms, there's worked examples, there's problem-solving strategies. All of those are good to read and review to get some idea what's going on. There's misconception alerts in the text that try to say, hey, people have an issue with this. Make sure you don't fall into that trap. There's these other things, simulations, blah, 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 blah. Your glossary and summary. You can read those and make sure you understand the vocabulary. When you do a flashcard, by the way, you should do flashcards if you're trying to learn something new. It makes it easier. When you start, do like 1 or 3 flashcards, and then as you get those, add one more, add one more, add one more, and so on as you study. Don't try to memorize all 50 flashcards at once. And then there's these end of module problems and these other problems here. Unreasonable results are things that you can think about when you're doing a problem. It says, hey, wait a second, this is probably not realistic. That's something you are going to try and get a feel for as you take this course is, does that seem reasonable? Get a good sense of that. Okay, so chapter 1 here, there's an introduction to physics in 1.1. There's about units and quantities in 1.2, and then a little on accuracy, precision, sig figs, and then approximations. One of the coolest things to get good at when you're a physicist is approximating things. We call it an order of magnitude estimation. Order of magnitude estimation. You know, you don't really care. Is there 1,000 marbles? Are there 10,000 marbles? Or 1,001, 1,024? You could say, well, there's about 1,000 or about 10,000, right? So the better you get at those sorts of estimations, the quicker you can make decisions in your daily life and in whatever you're trying to do, because you get good at practicing estimating things. Okay, how many hot dogs you need at a party and things like that, very important things. Okay, so this introduction to science is chapter 1 here. This talks about, this is the Andromeda Galaxy, and this is a picture, it looks like mostly in infrared. You know, hundreds of billions of stars, 2.5 million light years away, and they're talking about how the physics there is the same as the physics here. So if you want to learn about Andromeda Galaxy, well, study physics here on Earth, because it tells you how physics on Andromeda works too. This introduction here talks about that there's this underlying order and simplicity to everything, and if you study that, you can learn about the nature of things. So it's like a very cool form of philosophy. And what you're trying to do is figure out what these physical laws are from these basic concepts, okay? So that's the goal here. Physics is the study of the motion, the interactions of energy, matter, space, and time, and it tells you, helps you understand cause and effect. When things happen, what happens? When you do this, what happens? And so on. That's the main goal of physics. Of course, there's applications of physics. Once you figure out the instruction manual, you can apply physics to different things. So you can have applied physics, you can have engineering and chemistry and things like that, all come from the fundamental rules of the universe. So what we're really trying to do is hack the universe, figure out how it works, make it do what we want it to do. So we're just not having to obey the way things are now. As an MRI allows you to look inside a person, microscopes look inside a cell, see how everything works, blah, blah, blah. Okay, models, theories, and laws, and experimentation. So there's a little bit of a history here. Marie Curie is one of probably the most famous scientists, physicists in the last 100 years or so. But so read about her, she's pretty cool. So a model here, this is really interesting because when I teach you physics, or when you're learning physics and when you're studying physics, everything you're learning is a model. We're using math to represent something that happens. And then you can have a philosophical debate about whether the model is the true thing or the true thing and the model, what's the relationship to that. It can get very deep. But a model is just, this happens, so I can use this math equation to represent it. The math isn't what's going on. The thing that's happening is the true thing that's going on. You're trying to model it with some math, but the model is separate from the actual thing, though it can be related. The theory, in colloquial terms, we think of a theory as I have an idea. My theory is, so in science, a theory is a well-established network of hypotheses that have survived many experimental tests and appear to always give the correct answer. So that's what a theory is. So make sure you don't intermingle theory and hypothesis in your not local, but in your regular speak when you're at parties and stuff, because a theory is a well-tested set of hypotheses. A hypothesis is, I have an idea, okay? A law is something like gravity, where no matter what we do, it's always there, and you have to obey the law. That's a physical law, okay? So there's different levels. You start with your model and your hypothesis, you build up to a theory, and then there's some things that are just laws that no matter what we do, you cannot escape them. Okay, so it goes through here, talks about the differences. The scientific method, make sure you understand what the scientific method is on a very deep personal level, because it's a wonderful tool for figuring out the truth. There's lots of ideas. When something happens, you can think, oh, well, the sun is not rising today. It went away at night. We better dance so it comes up the next day. You can imagine that someone could convince you, if you're a baby, you have to go out and dance every day, because if you don't dance, the sun will not rise. And you don't dare not dance, because why would you not want the sun to rise, right? So the scientific method is a way to, you could say, well, okay, maybe I'll wait 10 minutes to dance. Maybe I'll just see, just for 10 minutes. No, you can't, you wait for, let me just do 1 minute. And if you just wait 1 minute and the sun rises, then you say your hypothesis is wrong. The sun will rise whether or not I dance, okay? Despite what I may want. Okay, so that's the scientific method. You observe something. You make a hypothesis. And the important thing is you make a prediction. You say, this, if my idea is correct, then this will happen. There's a consequence of my hypothesis. And then you do the experiment. And then, if the experiment is true, you win a prize. If it is not, you start over and try again. Okay? So we refer to a period pre-1905 or so as classical physics, and then after that we consider it modern physics. There's some famous people here. Here's a sheet of gold atoms, which is pretty cool. Okay, so you should know that classical physics is mechanics, thermodynamics, things of that nature. Modern physics is quantum mechanics and relativity, things of that nature, and they're kind of divided into two areas because of the mathematics. They're just different math. Okay, so that's your history of physics there. Read about that, get a sense of that, what they're talking about there, because that's really cool, and it's really important for building on the next stage. Okay, so 1.2 is on physical quantities and units. A physical quantity is a thing like a meter or a kilogram, a kilogram, or a dollar bill, okay? So these physical quantities, like mass, we describe them in terms of units. So, oh, sorry, did I say physical quantities are kilograms? So the units are the kilogram. The physical quantity would be mass. Okay, so let's say we start with a physical quantity, and let's say I have a pile of marbles, and I want to measure the marbles and see how heavy they are. So I put them on a scale, and I measure their mass. So the quantity that I'm measuring, I'm going to express it in units, and it could be kilograms, it could be pounds, it could be ounces, it could be grams. All of those are units to measure mass, which is the physical quantity we're interested in. Another physical quantity might be temperature, and you can measure temperature with Celsius or Fahrenheit. Okay, so notice the connection between physical quantity and units. Your physical quantity can be expressed in different units. So speed, velocity could be meters per second, or miles per hour, or kilometers per hour, but it all refers to the same physical quantity. Okay, so the fundamental units that we're going to use in our class is, we call it meter MKS units, meter, kilogram, second. Okay, so if you ever hear MKS for short, that means your length is meters, your mass is kilogram, your time is seconds. Okay, those are your fundamental units that you can describe other things. Derived units, let's see, hold on. Like the electric current is the ampere, and an amp is current, electrons or charge per second, something like that. Okay, so these are, electric current would be well, it's named after a guy named Ampere, but that's amp. Okay, so these fundamental units are the units like meter, kilogram, and second. Then you could have derived units like velocity, which would be meters per second, and those are called derived units. The second is defined as the time it takes for a certain atom to do a certain thing. Let's see, 9 billion vibrations gives you 1 second. So that's how we've defined what 1 second is. It used to be, you know, just snapping your fingers every time your heart beat or something like that would be a second. But now you've got 9 billion of these oscillations so that everybody can agree at every lab how long a second is. The meter is defined as the time it takes to travel a certain number of wavelengths. It's crazy. So it used to be this like hunk of gold that was sitting in France somewhere or something like that, and we decided, okay, well, we need a little bit more defined thing like that. So now it's the distance light travels in this many seconds, and that's the definition of the meter, so that everybody can agree on how long 1 meter is. We don't have to keep going to France and comparing yardsticks. Okay, so those are your units, okay? You got your meter, your kilogram, your second. Those are MKS, the fundamental units. There are ways to write numbers. Let's say I have $100. I can write it as $100. What if I have $1,000? I can write it as 1K. What if I have $10,000? 10K. Okay, we can simplify our, so we don't, I mean, physicists are lazy as anyone. So I don't want to write 10,000 over and over again if I can just write 10K. Okay, so I'm going to write 10K because it's shorter. That K just hides 3 of the zeros, so I don't have to keep writing them. I could also write it as 10 to the 3. That's 10,000. or 1,000 actually. So these are the orders of magnitude: 10 to the 1, 10 to the 2. So 10 to the 1 is just 10 to the first power. That's 10 times 1, so it's 10. 10 to the 2 is 10 times 10, so that's 100. 10 to the 3 is 10 times 10 times 10, so that's 1,000, and so on. So we can write 10,000 as 10 times 10 to the 3. For example, that would be 10 times 1,000, or 10,000. Or we could write 1 times 10 to the 4th. That's 10,000. Those are different ways to do that. Play around with those numbers. Try to do that. Try to write this. So 450, we can write it as 4.2 times 10 to the 2. 4.2 times 10 to the 2. 10 to the 2 is 100. So 4.5 times 100 gives you 450. So that's just shorthand. Sometimes you only care about what the numbers are, and you're less concerned about the order of magnitude. Other times, vice versa. Okay, the diameter of an atom, for example, is on the order of 10 to the minus 9 meters. That could be 1 times 10 to the 9 minus 9. It could be 1.5. It could be 0.8. It's on the order of, so it's about times 10 to the minus 9. The diameter of the sun is on the order of 10 to the 9 meters, okay? 1 billion meters, something like that. So, again, these are just your units. All right, so here's your prefixes. Your symbols here, you can have, you know what a centimeter is, a tenth of a meter. A millimeter is 1,000th of a meter, and so on. A micrometer is a millionth of a meter. A nanogram is 10 to the 10 to the minus 9 grams. You could also have a nanometer, which would be 10 to the 10 to the minus 9. So, you know, these are just examples of different things. Exa, peta, tera, giga, mega, kilo, hecto, deca, deci, centi, milli, micro, nano, pico, femto, atto. These prefixes just hide the numbers. Okay, they're just short for that. So 10 milligrams of something would be 10 times the 10 to the minus 3 milligrams. So that would be a flea. Okay, the mass of a flea. Let's see. Oh, actually, that is the thickness of a flea. All right. There's some cool stuff here. So, unit conversions. So, if I want to convert, let's say, miles per hour and convert that into meters per second. Okay, so that's short for meters per second. I'll write it like that. Okay, so I'm going to have miles. Let's say I go 70 miles every hour, okay? And I want to get into meters per second. Well, I'm going to multiply it. I could do my first thing to get into seconds. So I'm going to multiply this. I'm going to have 1 hour, 60 seconds in 1 hour, right? Oh, sorry, 60 minutes in 1 hour. So I'm going to have 1 hour, and for every hour that I have is 60 minutes. And then I'm going to have 1 minute for every 60 seconds. If I do that, then this cancels out. This cancels out. I drew this as minutes instead of mins. Don't want to confuse you. Mins, okay? And that times that times that. So that gives me 76 miles divided by 3,600 seconds. Okay, so that would give me whatever that is, 76 divided by 76 divided by 3,600. So if I'm going 70 miles an hour, that would be 0.02 miles per second. Okay, so every second that goes by, I'm not traveling many miles, only 0.02 miles per second. And then we've got to know the conversion factor from miles to kilometers. Okay, and there are 1,600 meters in a mile approximately if you ran track, or 1.6 kilometers in a mile. So that means I'm going to multiply this by, because I want meters at the top, I'm going to have 1,600 meters divided by 1 mile. Okay, and cancel that out. So times 1,600 means I'm going about 33 meters per second. Okay, so that's how you could convert units. The important thing that you should be thinking about when I'm telling you this stuff is that the number and the unit go together. You can't have one without the other. The other thing is that if you get your units right, called dimensional analysis, if you have your units right when you're doing your equation, you'll probably have the right answer. Because you cannot get the right answer if your units are wrong, for sure. And the odds that you have the wrong answer and you have the right units, very slim, or you might be off by a factor of 2 or some other random number like that. So some conversion factors. So you can convert from inches to feet. There's 12 inches in a foot. You can convert from centimeters to meter. There's 100 centimeters in every meter. So if I say there's 2 meters over here, you could automatically go, oh, well, that's 200 centimeters. If I'm like, oh, movie's 2 hours, you know automatically there's 120 minutes in it, right? So these are your conversion factors, but the important thing is that the number and the unit go together, okay? So here's some other examples of different lengths. You can go through those if you want. Okay, so here's some unit conversion examples. So study these. So suppose you drove 10 kilometers from your home in 20 minutes. What's your average speed? That's just rate times time is distance. So your average speed is distance over time. And we want to figure it out in kilometers per hour and meters per second. So we're using our rate times time is distance equation here. And then we say that our average speed is 10 kilometers over 20 minutes. So that means half a kilometer per minute. And now we need to go from kilometers per minute to kilometers per hour. But there's 60 minutes in every hour, so we can multiply those together. Our minutes are going to be canceled out, and we're going to leave our hour on the bottom half here. And so that'll give us our 30 kilometers per hour. If you want to go to meters per second, do the same thing. Try to do that on your own before looking down here at the answer. Okay. Okay, accuracy, precision, and significant figures. This is pretty cool. So the accuracy of a measurement, the precision of the measurement are a little bit different in what their ideas are. So let's say you have a target, and let's say you are playing darts, and you hit a dart, and hit it over here. Okay, well, that is kind of off the center mark. There's your bullseye. You hit it here. Let's say you threw another one. Ping. You hit another one. Ping, 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 ping. And you kept throwing darts. Well, they all ended up over here. Okay? This is not a very accurate toss, but it is a very precise toss. So you weren't very accurate because you were trying to hit it here. But you were very precise in your tosses because you were off by the same amount every time. So it's very precise, but it wasn't very accurate. If you were neither precise nor accurate, your things would be random. But since they were all nicely bunched there, it's pretty precise. Okay, so that's a subtle thing. Make sure you read this and understand the difference between accuracy and precision. Very cool, actually, what it comes down to when you study these things. Okay, and here's your example of these bullseye thing. Okay. One of the most important things in science and life is the uncertainty in your measurement. Okay? The uncertainty in your measurement has to do with how precise and accurate your measurement is. Okay? So whenever you conduct an experiment and you get a result, the most important value in the measurement is actually the uncertainty. It's not the measurement itself. Because the measurement itself is worthless if you don't understand your uncertainty. If you measure the temperature in a room and you say it's 48 degrees in here, okay, well, let's say it's comfortable. It's 70 degrees in here, okay? Well, plus or minus what? Well, okay, if it's plus or minus 1 degree, then you're going to be pretty happy because you know that 70 degrees is comfortable, and you know that whether it's 71 or 69, it still makes for a comfortable atmosphere or environment. Okay, so If, however, your uncertainty is 20 degrees, so you say, yeah, it's 70 degrees in my room, plus or minus 20 degrees. So it could be 90 degrees or it could be 50 degrees. So in one case, it'll be sweltering hot. In the other case, you'll be freezing, okay? Or at least, very cold. So the uncertainty is very important. What does the uncertainty come down to? It comes down to the precision of your meter stick. So if you have a meter stick, the fundamental unit on it is a millimeter. That's as best you can do with your accuracy and precision. Okay, you can't get more precise than a millimeter. Okay, so you got to make sure when you're making measurements and trying to estimate things that you are understanding things that contribute to the uncertainty in your measurement. Your measuring device could be only as precise as 1 millimeter. So you better not put down 4 significant figures, 11.224444 meters, if your meter stick only goes to millimeters. If you have shaky hands, then you're not going to be able to make a good measurement there. If the object you're measuring is hard to measure, there's going to be some uncertainty from that. Anything else, maybe you bumped it while you were measuring it, or who knows. Okay, all of those things prevent you from getting a precision better than 0.1 inches. Okay, and so your uncertainty on that measurement, you can't know it better than that because your apparatus doesn't allow you to know it better than that. Okay, so your uncertainty is a very important thing. Here's some percent uncertainties here. Okay, uncertainties in calculations. So yeah, let's look at this one. A high school track coach has just purchased a new stopwatch. The stopwatch manual states that the stopwatch has an uncertainty of plus or minus 0.05 seconds. Runners on the track coach's team regularly clock 100-meter sprints of 11.49 to 15.01 seconds at the school's last track meet. The first place sprinter came in at 12.04 seconds. The second place sprinter came in at 12.07 seconds. Will the coach's new stopwatch be helpful in timing the sprint team? Why or why not? The solution is no, because the uncertainty on this measurement is 12.04 plus or minus 0.05. Same thing with this one, 12.07 plus or minus 0.05. These two numbers are statistically equivalent, okay? This could be 12.09 or it could be 11.99. This one could be 12.12 or 12.02. So they overlap each other in their uncertainty. So they're, as far as we can tell, equivalent numbers, because the time given by the stopwatch could be wrong. Okay, we can't tell who's who from the apparatus. It's not precise enough. Okay, so that's what that's getting. That is the most important measurement number in science, is your uncertainty. So a lot of times we hear things about public opinion polling and things like that. Those have huge uncertainties. They have uncertainties of 5% usually, plus or minus 5%. So if you got 45% on one thing, 48% on the other thing, it's hard to differentiate between the two. Those polls may as well be telling you the same thing, okay? Because their uncertainties overlap. All right. Yeah, so keep reading that. There's more about significant figures here for calculations. Important stuff there. All right. You'll get really comfortable with this as we go through the course. And then approximation. This is really cool. Approximation is something you really get good at. It's a guesstimate. It helps you understand when you're doing physics problems. You can get an idea whether you're on the right track by just looking at the numbers and get a sense of the scale and be like, hey, does this make sense? So I definitely recommend you practice doing that when you're doing your whatever your homework problems you're working on. Just make sure it seems like it's making sense as you go through it. Okay. Yeah, there's some examples here of trying to make some estimates. So anyway, read through those. Okay, so our summary here. Physics is the study of energy, matter, space, and time, and what happens when things do things. Physical quantities and units. Quantities are like mass, length, time, and then we have units that we can express the quantities in, like meters, kilograms, seconds, millimeters, micrometers, pounds, feet, whatever. And then you can convert from one to another. And then accuracy, precision, and significant figures. Make sure you know the difference between accuracy and precision and why that's important. Significant figures is, when you make a measurement, you try to express it in your most precise value, and then the most precise number on your number tells the world your precision and how much you believe in it, basically, or how well you understand that. Okay, and then approximation. As you work through your problems, try to see if your answer is starting to make sense, and you try to develop an intuition for some of these quantities. Okay, see you guys later.